Hello, Georgi Romanic here. In today's video we are going to calculate geopotential of a sphere. In my last video I derived the concept of geopotential and equation for geopotential. As I always say, it is important to know how to apply this concept. And to do that, we will assume that our beautiful planet is a perfect sphere, mass is uniformly distributed throughout the sphere, and the only other thing that we need to know is Newton's law of gravity, and I have videos on Newton's law of gravity. So, using the assumption that planet is sphere and using Newton's law of gravity, we can calculate the lines of constant geopotential around that imaginary Earth. Let's do it. Okay, to find geopotential of a sphere, we start from the definition of geopotential, that is phi is equal integral g dz, and that needs to be integrated from 0 to z because 0 is reference height. Now g is function of z, and how it depends on z is explained in my video on Newton's law of gravity, and we know that this g, small g, is actually capital G, which is universal gravitational constant, mass of Earth divided by the radius of the Earth plus z, the everything squared dz. Because they are true constants, I can also put them in front of the integral and write gme integral 0 to z dz over re plus z squared. Now I would like to mention that mathematicians would not be happy about my writing style, because they would say you have to put some prime over here or something, because this is dummy variable and it should not be exactly the same as the variable in the integration, but these are just formalities, it doesn't matter. Now, how do we solve this integral? Well, actually this is very simple integral to solve. We will introduce substitution. We say some u, let's say, is equal re plus z, what we see under the integral. And if we differentiate this, du is dz, because re is constant. With this substitution in mind, this integral becomes phi is equal g me integral dz is du divided re plus z is u, and there is this squared. Now, what are the limits of the integral? When z is 0, u is re. When z is z, u is re plus z. This is now table integral because I can write this as g me integral re to re plus z u to power minus 2 du. That's the same. And now I can finally solve this integral, and of course the solution is g me u minus 2 plus 1 divided by minus 2 plus 1. This is how you solve integral with the power. And the limits are re plus z. I'm doing this a little bit more detailed than perhaps I should, but perhaps some of you are not familiar with integrals, and this is good practice for you. Now, when I insert these limits, my geopotential phi, and let's put here S of a sphere, is minus gme 1 divided by re plus z minus 1 over re. Now, something remarkable. Look at this. If we say limit when z goes to 0 of this phi s, what is it equal? When z tends to 0, this one tends to 1 over RE, and then 1 over RE minus 1 over RE is 0, which means this whole thing is 0. And this makes sense. If we are on the surface of the sphere, we are at the 0 geopotential plane. Makes sense. Now let's see what happens when z tends to infinity. If z tends to infinity, then this one tends to 0, 1 over infinity is 0, minus and minus give plus, and this becomes g me over re. And that also makes sense, because if we want to go to infinity, we need to beat, so to speak, the entire gravitational potential field of this sphere. Nice integration, geopotential around Earth. Until next video, goodbye.